Okay. Okay, I think I can show you. I think the paper is listed yesterday. So it is there. I'll show you. Okay. So it's like at the bottom. You see that there is always. Yeah, I'll show you. I know what you. So you did run two papers. There were one was the iteration one, and the other one was the discrete time. Travis, I'll show you that. So right. There are that's in the paper. Yeah, I gave you more examples you can play. So, but the code runs and all that, right? Yeah. I just want to make sure. Yeah. So the best is to play with it, and we'll talk about it because those are reinforcement learning stuff. Okay. All right. Okay. So just for motivation, yesterday, remember I didn't show you these plots. One was traditional control schemes cause instability. Now remember we talked about it. I didn't show you. Because remember, the reason it causes instability is primarily because the A matrix and B matrix get changed. And it has the random variables, the delays and stuff, remember? So that causes instability if you ignore it. Okay? And in general, people know that for control systems, delays causes havoc. So here it's a random delay, not even deterministic. So that's the main thing, and you can see there are two plots. One was there is no delay and losses. If I take the original system without the network, it nicely converges. Now the same system, now I have the AZK, BZK, things will blow up. You can do the simulations very easy. Okay, number one. Number two, now optimal design, we talked about it. Right? If you're using optimal control or nonlinear control, they require the system dynamics. Right? We also talked about it. And since the delays and packet losses are random variables, and they are part of the A and B matrices, you don't know those, you only know the distribution, even that is an assumption. So as a consequence, you don't really know A and B if it's a linear system. Okay, and the other thing we also talked about is the traditional optimal control works backward in time. I explained to you, and it requires full knowledge. Where we already talked about it, right? So those are okay. All right. So we also talked about we are going to use adaptive dynamic programming because the dynamic programming requires the dynamics. It is another way of coming up with optimal control, right? Whereas the dynamic programming is the other way. One is the calculus of variations. That's the old method. Dynamic programming was developed in 1950s by Bellman. And so we are going to use dynamic programming. It's a lot easier because that helps us to look at the temporal difference error. We're going to talk about that, which is used to design controllers. Temporal difference error comes from reinforcement learning. Okay, this is how you bridge that. The reason it's called adaptive is because system dynamics are needed in traditional dynamic programming. But since we don't have it, we are going to have some sort of adaptation, and that's why it is called adaptive dynamic programming. All right? So here is a basic thing here, a flow chart. You see that how we are varying this. This is the temporal difference error, and then you're using the value function. So this is a traditional policy and value iteration, that one of the papers. This is the paper that simulated, that policy and value iteration. And the thing is, there is a drawback. Okay, so there's a drawback. Remember I told you about the Riccati equation or the JB equation. There is no closed form solution. So you use the policy numerical methods, you hold the sampling interval, and you are iterating within the sampling interval. Now you really need to have a significant computing power, because to find a solution, we don't know how many iterations you need, okay, to solve that equation, which is Riccati or okay. So as a consequence, what happens is the papers that talk about that approach, they really don't consider the real-time effects. Okay, so we used time rather than that. So you can see also, if I'm taken one of the problems, if I use 1,000 iterations, it nicely converge. But if I change it to 10 iterations, things will blow up. You see? So what does it tell you? It tells you that the solution is not complete, and if you stop it halfway through, the numerical analysis methods diverge rather than converging. So this is the problem. Okay? So we don't want to use it, and we don't know if the system dynamics are unknown. I don't know how many iterations do you really need. So those are the reasons why we use the time method. Okay? So I also gave you a slide. This is the paper, 2012. The one that I gave you. Okay? And I think in the slides there's also, I listed them. Intro to oral. If you look at the intro to oral slides, you will see that name, Dirks and Jagannathan, 2009 or 2012. Yeah, that is the paper. It came out in Transactions on Neural Networks. Okay? So you can see that people were using policy iterations. So in 2012, we used what we call time-based. So basically, we don't use iterations. We update the weights once a sampling interval. And we make sure that it converges and the optimality is reached as time goes to infinity. So there's a difference. Okay? In their case, you can make it optimal along the path. In our case, it takes a while. But in practice, what we noticed was you really don't need a very long time to converge. It converges very quickly. So this is the benefit actually. Okay? So this is what we call time-based. It's a traditional adaptive control approach. Okay? So that's what we are doing. And we also talked about, you see this picture where you had delays and packet losses and all that. And we also talked about issues, right? One is the network-induced delay. Either constant or random, right? It is a problem. We also have packet losses. And we also briefly talked about network protocol effects, right? And we did TCS and so network imperfections cause uncertain dynamics, whether it's a linear system or a nonlinear system. Okay? And I won't go through this. You can read them. Transmission delay is a big challenge. Okay? And it takes, you see that from the top to the bottom, it takes from the sensor to the controller and from the controller to the actuator. It's a round trip time, right? And packet drops are another bigger problem because the data from the sensor doesn't reach the controller, and from the commands to the actuator may not reach the actuator. Okay? So there is a problem there. Okay? This issue is fatal. And so that's the issue there. Okay? And timing is an issue. So we talked about there are two protocols. One is the TCP/IP, which is used in the internet. The other one is called UDP. Okay, UDP doesn't have a feedback. So the question is, how do the protocols dictate how much delay you need, what information is available. We can use that information as part of the controller. Okay, and the other thing we talked about is the quantization. I know somebody asked the quantization, and it clearly says quantization is basically you don't have infinite precision. Okay, and remember we use A to D and D to A hardware even now, and when you are using those devices there is a finite word length, and it takes a number, it converts into number of digits, right? There's a round off and all that problems, and that can cause problems. It's proven actually. So read this part. Okay, so what happens is you see there is a quantizer on that side and there is also a quantizer on this side. And there are two quantizers typically. One is static, where the range doesn't change. The other one is dynamic, where the range you can change it by using a zoom parameter. And so the benefit is the dynamic is it basically can go as much you want and you can show some nice properties with it. And so we're going to look at that, and there's a MATLAB code you can play with it. Okay. And now here is the protocol effects. All this stuff we have talked about it. So here is the AZK and BZK that we talked about it yesterday. So here you can see this is a TCP. And so this is a TCP, this is a UDP. So in a TCP, you get the measurement output. This is the delay, this is the loss, packet loss, delay, and this is the feedback. So there is always a feedback from the protocol that's used to the observer. Because you don't have the states, you have to use an adaptive observer. So observer, what does the observer do, guys? It estimates the states, some of the states. That's what it's doing now, okay? So that estimated state is basically goes to the controller, and the controller basically goes through the quantization and everything. So this is TCP. TCP provides a feedback, not every instant, but so many packets, even for the internet also. The same thing happens. It's an end-to-end protocol. So it goes all the way to the end, and then the feedback comes back. But a lot of times that feedback is delayed. It takes a long time. So if you take a course on computer networks, you know that there's a delay. It's an end-to-end protocol, okay? So this is UDP. This UDP is usually designed or used for sensor networks. So when you have a sensor with a wireless connectivity, the sensor is sampling at a very high frequency. There's no reason for us to have a feedback, right? Even if you miss, because let's say you're measuring temperature. The change of temperature over time is not fast. So you can lose 1 or 2 packets, okay, and still reconstruct the actual signal. So in a UDP, you see that there's no feedback, and so this is the UDP information, you know, and UDP is used for sensor networks and stuff like that. There are a lot of different applications, okay. Now there is also difference between network control systems and stochastic dynamical systems. A lot of times people have that problem, right? So modeling, so when you say stochastic control, this is very clear. You got to realize that. If you have taken optimal estimation, anybody has done Kalman filters? I see many people. But I know you guys don't do the derivation. Did you look at the derivation part of the Kalman filters? Okay. So there it's basically done in stochastic. So the difference is the system is deterministic. I don't know whether you noticed that. You add a process or a measurement noise. That makes the whole system stochastic. But here, the actual matrices A and B contains the random variables. This is a fundamental difference. A lot of people don't understand that. So, and you saw that in the derivation where A and B becomes a function of, you know, the actual packet losses and stuff. So if you look at Kalman filter, the way Kalman did is you took a deterministic system A and B, and then he added the process noise and Y, you have the measurement noise. Since process and measurement noise are white noise and it's a bunch of random variables, the overall state becomes random. And therefore he is looking at average values. It's a lot different with NCS. So you got to be careful understanding that. Okay, so that's the difference here. And the other one is in the NCS case, the ultimate system is time varying. Now why is it time varying? Because of the delays and packet losses. They are varying with respect to time. Okay, and you can also include process and measurement noise even if you want it. So there is an extra term in the derivation that pops up, and I'll show you extra term. But otherwise, the optimal control policy, everything is identical to the deterministic system. Okay, so you can remove the process and measurement noise, but still the system is stochastic. Okay, so you see that addition of process will have additional terms for stochastic Riccati equation. So that's basically a little difference between that and so here is the general stochastic optimal control under TCP, under UDP. So here you are using the psi. The psi is basically the protocol set, and is a zeta. That's the protocol set under UDP. So it's a conditional probability. Now the other thing I wanted to tell you was, if you remember, we study what we call controllability and observability. This is a very important result in control theory that does not exist, which we need to be proud of. It doesn't exist in a lot of things. Now, I know a lot of people don't understand what that physical meaning is. Can somebody tell me what is the controllability meaning? I know how to check it. I ask my students, immediately they write those equations. What does controllability mean? Uh-huh. Mm-hmm. See, that's why I asked that question. I'm telling you, these things you probably, that's what, remember yesterday I asked you, what is the difference between? So anybody has a better answer? I'm telling you, I have went through so many countries, people still don't understand this. There's a physical meaning, actually. So, anybody want to take a guess? So, well, let me say, I'm going to give you a homework. I want you to come back tomorrow and tell me the physical meaning. Guys, you need to know this. It's just not a piece of math. You have to have a piece of math, but it has to have a physical meaning to it. What is controllability and what is observability? In a very layman language. That's all I wanted to. And why do I care? Okay? So, but here what I wanted to show you was, if the original system is controllable and observable, we have proven that the network control system will also become observable and controllable. Okay? So that's the derivation that is there. I'm going to skip it. As I said, it's in the book. Okay? So that is important, because without that, we really cannot design anything, right? So that's very critical. But I want you to, before I answer that question, I want you to do a little homework for me. And you explain to me, as if I'm your student, what is controllability in a very layman's language and what is observability. Okay? Huh? That is what it means. But what is the physical meaning? So what will happen if I don't look at it? You know what I mean? Yeah. That's what I want. And what does observability mean? So physically I need to know, let's say if you are from industry like him. Yeah, he will ask the question, why do I check it? Right? Make sense? I'm from industry. I need to know really, why do I care? I don't like the math, so why do I care? So let me ask you, let me rephrase it. So let's say if the system is not controllable, what does it mean? It doesn't matter. Doesn't matter. If the system is not controllable, that's what it means. I'm just telling you. You're repeating it in a different language. So if the system is not, if it's not controllable, so what does it mean? Yes. That's what she said. Yeah. Okay. You can always Google and stuff, right? I think these are the in-depth understanding. It's very needed. Okay. Okay. So, any case, so what this derivation is showing is, if the original system is controllable and observable, you can prove that with the NCS dynamics, the network, you can also show the system is controllable and observable. So that stuff is in here. Okay, so you can, I will skip the math, but here is the math to prove that it is, with some Markov parameter, Topolis matrices and all that stuff. And finally, you can show that the system that with the AZK and BZK is also controllable and observable. Okay, this is to rigorously prove that we can do something with it. Okay, I won't tell what it is, but all right, you can do something with it. Okay, so that stuff is there. You see, there's a lot of math. I won't go through this, otherwise we won't have time. All right. So this is the distributed network control systems. We're going to look at it, where you have a shared communication network, okay, and you have multiple controllers and actuators. Now, what are the applications? We talk about smart grid. Remember that. Or you can talk about the CAN bus on an automotive system, controller area network, where you have different subsystems use the same common bus. All right. So that will do, I think, in chapter 8 or 9. At the end, we will deal with those. All right. Any questions here, guys, except the controllability and observability, which you can tell me? Yeah. So the UDP is used if you need some sort of an acknowledgement. So UDP provides an acknowledgement. Acknowledgement is basically what happens is you have a big packet in the internet. Yeah, handshaking, yeah. So what happens is that it's an end-to-end. So you send your message will be divided into a bunch of packets, right? Each packet has a number, specific unique ID. And that goes, and remember, the internet routing, it can go different routes. And then what happens is when it reaches the destination, there is the scheduler, it looks at the ID and it rearranges that in a proper manner so that it reconstructs the message. This is how we do our emails and all. Okay? So what happens, because the routes can be different based on the real time, okay, in the internet routing, So whenever a packet comes, depending on the TCP parameter setting, you can get an acknowledgement to the sender, every packet it receives, or once in so many. The purpose of the acknowledgement is to retransmit or not. So TCP has a feature called retransmission. So if the acknowledgement was not received within a time window, that's another parameter. Okay, by the sender machine, it retransmits. You see, and what is the purpose of retransmission? Because let's say if that packet, one of the packets in the message get dropped. Let's say you have a long email you have written, and that is translated into, let's say, 100 packets, for example. And the sender machine will keep sending the protocol. There's a protocol running on the sender. There's one running on the receiver side. So destination. So what happens is the sending one will be sending, and it takes different routes. So assume that one of the packets get dropped. So the ID, it checks the ID and it knows the sequencing. And what it does is, depending on how you set the internet parameter setting, it can send an acknowledgement every packet it receives. And that comes back through a different route to the sender machine. So if it didn't arrive within the time frame, then the sender machine will keep sending those acknowledgements. So there is a drawback for that. That's why the UDP has come. What is the drawback? Because imagine your network is being congested. And when because of the congestion, it takes longer to get acknowledgement. And if you don't properly set it, your sender will keep sending those packets. It creates more congestion. So TCP has the transmission, that retransmission property. UDP doesn't have it. Because the purpose that is because like sensor networks and all, you will be sampling at high frequency and you are transmitting large quantities of data. Network gets even more congested very quickly. So they don't want to have it like a lot of control applications. If you lose a packet, you're okay because you have enough sampling frequency so that you can manage. That's the main reason why you do that. So yeah, I have taught network courses. So and as I said, my master's is in ComSci. Yeah, so this is very critical. This is very important. You need to know, but it's not that difficult actually, the networking course. Okay, all right. So any questions here, guys? I think this is my last slide. So I just want to give you. There are a bunch of slides at the end. Read them. Gives you some basic things, some of the differences, what are the challenges, and quantization can also cause instability. So quantization, random variables, all that network-induced delays, they can cause and destabilize the system. This is why we are doing it, okay? All right. So that's number one. This is lecture one, like yesterday we covered. It took half an hour. I thought I would finish in 10 minutes. All right. Okay, so let's go into Lyapunov stability. So remember, as a control thing, it's very critical that we show some stability. Because of time, I will skip a few things and we'll go through, I encourage you to go through the book, some of the basics on stability, So you have a system, you can draw the block diagram. Here is a nonlinear system, Y is the output, okay? And you can write it in a Bronowski canonical form. x1 of k plus 1 is x2, x2 of k plus 1 is x3. So this is very typical with any of those mass damper systems. You remember F equal to ma, right? x1 dot equal to x2, x2 dot equal to, F over m, right? So things like that, and you can see this is what they call Bronowski canonical form. And you have a linear system, and here is a solution in discrete time. X of k is, A is the state transition matrix, a to the power of k times x of 0. That is the response due to initial condition plus response due to the forcing function. There is a u is basically the forcing function. Okay? And there's an example, I encourage you to go through that. It's not that hard. Savings bank account. All of us have an account. How the interest gets compounded. You can use this simple things. Okay, there's a little MATLAB code. You can run it. And there's also norms. How many of you studied norms? A little bit. So there is a lot of stuff in there. The other books, if you look at my name, there are other books have a lot of details about the norms. Okay, so there's one norm and stuff. Why do we need the norm? Why? That's why I said, yeah, why? Another homework. Go back and look at it. Why do you need that? I think these are important. It's because you might know where to use or what to use, but you never really spend time, okay? So this is one norm. One norm is absolute value. Two norm is the Euclidean norm, which is basically the distance, okay? So infinite norm is the maximum. There are physical meaning behind it. So there's one is the mathematics. So that's not enough. That's what I keep saying, that just knowing the math operation. So you need to know what is the physical meaning in there. Then only you can answer that question. Why are they using infinite norm or Euclidean norm? Yeah. So, yeah, unfortunately we cannot cover all this. That's why. So here I gave you the pth norm, the infinity norm. You see the maximum operator equation 2.110. Then you have the matrices also. You can actually do what we call induced norms. And in a matrix, so you can put them as a basically a vector, and then you can do the same. And you can see there is an infinity norm, there's a pth norm, and there's also called Frobenius norm. Normally in neural networks we use the Frobenius norm, and that's square root of A transpose A. If A is a matrix, and A doesn't have to be a square matrix. Because you multiply A transpose A, like you said, there's singular values pop up because it's not a square matrix, it's a rectangular matrix. The rank of the matrix, when you multiply changes and you might have zeros. So those things will pop up there, So Frobenius norm is what we normally use for neural networks because those weights typically are not square. They are basically rectangular weights, mostly rectangular matrices. And so we use Frobenius norm, okay? So all that stuff is here. You see that Frobenius norm is trace of A transpose A. Now, why is the trace operator there? So go back here for a vector. You see that's one norm. So absolute value of each of the elements, and then I'm summing it up. What is the outcome? It's a scalar or a vector. And is it positive or a negative value? And why? I know that absolute is there. But why is that you always want to have an absolute and it's positive? That's my question again. I know it's absolute is there, so it is positive. And why do we care? All norms are always typically positive. Okay, another homework. Go back and look at it. And check and see why norms, why do we use norms, and why it always a positive. Okay, there's a reason behind it, okay? All right. So there's a quadratic forms, like I think that's what you are saying. If X is a vector, Q is positive definite, positive semi-definite, there are definitions here. Negative definite, negative semi-definite, because you use those in your Lyapunov, okay? And then here is a quadratic form, X transpose X, Q times X basically is greater than sigma min and less than sigma max. Sigma is a minimum singular singular value. Now what is the difference between singular values and eigenvalues? What are eigenvalues? Okay. Lambda I minus A equal to 0, you might have done that, right? I want you to check what is the difference between singular values and eigenvalues. That's another one. Okay. So singular value decomposition, essentially you can take a matrix and you can divide that by using 3 different matrices. Okay, you can see that there is 2 matrices U and V. These are singular directions basically, and then you have a matrix which is sigma, which consists of all the singular values, and you can see zeros, and that can give you the rank and so forth, right? The eigenvalues and singular values. I want you to look at these actually, okay? And normally when we design controllers, you have certain properties on the nonlinearities. One of them is Lipschitz continuous. So we talk about this, what is Lipschitz continuous? Basically it means that it's differentiable and that derivative exists. Now why do you need that? Now why do we need all this? Remember, we do this in calculus. Okay? So why do we need all this stuff? Why don't we just ignore it? Yeah, I should be able to say that. Why Lipschitz and all, why do we care? I understand that. That is right, that's what you do. But why do we check? Why do we need to check? That's my question. Okay, homework. Okay, so we need to check it, but my question is why? Why do we care? All right. So here you can see that you basically show that you take x-axis x and y, 2 points, and then you try to find the values, corresponding values, f of x, f of z, and then you find that, and that basically looking at the slope if it's a two dimensions, right? And so that's basically Lipschitz constant, but then there's a reason why we do that, because we have to make sure that certain properties are satisfied. Okay, so I want you to tell me that, when I say it's basically the meaning, these are the things you stay with you. And I think if you remember this, it's not the number of courses you take. Education is a component that stays with you even if you leave the portals of a university. Remember that. So I may not know exact derivations because I can't keep up, right? But I'm able to give you or understand when somebody is saying why this and why that. That's very important. Yeah. Okay. So uniformly continuous. So continuous is one thing, uniformly continuous, right? So the higher derivatives exist and is also smooth. And these are required. And there's a reason why we need that. The same thing in discrete time. Okay. So take a look at it. Okay. And there are a bunch of stability conditions. Asymptotic stability, Lyapunov, boundedness, all right? And boundedness means that, you can see that here is the bound and the system trajectory, and it takes a time t naught is initial time, capital T. Within the capital T, the trajectory has to come within the bound. Now, why is that boundedness more powerful than asymptotic stability? Because this I can tell you, the reason why asymptotic stability is not preferred is only a theoretical result. Typically, it's very difficult to prove asymptotic stability, especially because you have noise, disturbance, there are so many things. So therefore, practical form of stability is boundedness. So you show that it's close to your, where you have to reach. And the size of the bound, you can actually control that. That's called UUB. If it's a purely Lyapunov stable, you will not be able to control the bound. So Lyapunov stability says L is positive definite, the Lyapunov function, L dot is less than or equal to 0. Okay? So unless it is less than 0, it's not asymptotically stable, right? But here, boundedness essentially shows that, but that's very theoretical form of stability. Okay? So here, boundedness is more important because there are so many different things you will end up in practice. UUB is more powerful than. So the same thing in discrete time. Okay, I'll skip the interconnected systems. In the nonlinear stability, remember that we talked about here. If there exists a Lyapunov function, the equilibrium point is stable in the sense of Lyapunov. Asymptotic stability is the first difference is negative definite, then it's asymptotically stable, and globally asymptotically stable is that function is global, and you have the constraint L of x goes to infinity as a norm goes to infinity. So that's the global. There are some examples. So try to work it out, okay? And those are important. There are a bunch of examples, okay? So these are homeworks that is given here. You can see that L is defined as x square plus x1 square plus x2 square. That's always positive for any values of x1 and x2. Then you take the first difference, and then you basically show that it is bounded or whatever, okay? Now, there's a huge difference between continuous time and discrete time. So that's my PhD work. When I was doing it, two things I've done. I made it very easy for people to do discrete time proofs. Okay? We won't have time to discuss this, but before that, people were doing breaking things, and there's a reason why, and I'm going to explain that very quickly. The second problem was the neural network, machine learning stuff, because I needed that stability to prove convergence. Okay? So now, what is the difference between continuous time and discrete time? So let's see. I don't know. There's no board here. I can write on it. Okay. So where is the pen? Oh yeah, that's good. Oh. Is there something I need to turn it on? Tap it? Is it? No. Yeah, pen. Select the pen. Yeah. Yeah, I think that's right. Okay, so you can see that for a screen we need so many engineers. All right. So in continuous time, remember that you select a Lyapunov function E is equal to E square, right? Let's say. And then you take the derivative V dot is 2 times E dot. So the V dot is more like a proportional to E dot. So it makes it easier when you are deriving update laws and adaptive control and stuff in continuous time. Now if you do the discrete time, okay, so let's say my discrete time function V is equal to E square of k, the same thing. So what is V dot in discrete time? Delta V. So what is delta V? Delta V is E square of k plus 1 minus of E square of k. So you can see that the first difference in a discrete time is nonlinear. In this case, it's quadratic. Whereas in the case of continuous time, it basically becomes a linear with respect to the first derivative. So what happens is, when you are proving stability in discrete time, you are dealing with nonlinear stuff. Everything gets squared, and it's very difficult to prove to show the proofs. So what they did before I got my PhD, in the case of adaptive control, they used to break that Lyapunov function into 2 parts. One for the error, one for the parameter update. In continuous time, you put together. And so when you separate it out, you have to use an assumption called certainty equivalence assumption. So I eliminated all that as part of my PhD. So and I showed how to easily do this discrete time proofs. Yeah, in early 90s. So those are the changes. That's why yesterday I was telling you, if you get a PhD, you have to have a mark on everybody should know you. So that's the basic thing, you know. So that's why in discrete time it's a lot harder to prove anything. Okay. Now, why is it important in discrete time? Because remember when we were taking the continuous system and we are adding those network effects, it ultimately becomes a discrete time system. Yeah, that's why. All right. So you study this and you see, you can see that the first difference becomes quadratic. You don't need the pen. Use the. I know, that's the other part. So then you show x1 of k plus 1, you know the dynamics, you plug it in and you simplify it, and you get that, and from there you show that norm of x is less than 1, and therefore you can say some stable, you know. All right. I don't know whether I can. This one? That's all you need. Okay. All right. So this is the global stability. So there are examples. Here you can, you know. Now, is this system linear or nonlinear? Huh? Is that system linear or nonlinear? Why is that so hard? So that's nonlinear, right? Why is it nonlinear? There's a quadratic term, but let's say if it's not quadratic. Let's say x1 times x2. Is it linear or nonlinear? Why? You have the product. Two states, right? Okay, so you can see that there are some proofs. And, you know, you can go through this, okay? And I also gave you the controller design, like here. There is an example, x1 of k plus 1 is x2 sine of x1, x2 equal to square root of x1, x2 plus u. You can actually pick a Lyapunov function L equal to x1 square, x2 square, the delta L, and then you plug in those dynamics, then you select your u of k equal to this, then you get first difference equal to minus x2 square of k. So that's negative semi-definite or negative definite? And why is it semi-definite? Huh? So x2, you know, whatever values of x1 is, x2 in delta L will become 0 only when x2 becomes 0, right? So it's negative semi-definite. So basically you can only show the system is stable in the sense of Lyapunov. So here is some other things that you know, for linear systems, this is the discrete time Lyapunov equation, A transpose PA minus P equal to minus Q. Continuous time is A transpose P plus PA equal to A transpose P plus PA equal to what in continuous time? A transpose P plus PA equal to in continuous time. So homework, go back and look at it, okay? This is the discrete time. And there are some other things here, you can look at it. So autonomous versus non-autonomous. So it's not the same as removing the operator. So non-autonomous means there is an explicit dependence on time. That's why you see a k there. And why do you get that? Because you might have a disturbance. And the disturbances typically are varying with respect to time. Okay? So here is the time varying definitions. So you can go through all that. This is the nonlinear side of it. And there's an Lyapunov extension we call the boundedness, UUB. So L is positive definite and delta L is less than 0 for x greater than R. That's basically the set R. Then the system is uniformly ultimate bounded and the norm of the state is bounded within the neighborhood of R. Okay, I'll skip all that. To have this can be deterministic. This W is basically either process or measurement noise. or a disturbance. Okay? And that's what causes the whole system to be stochastic in traditional stochastic control. And typically W is the Gaussian process random variable representation. So you see that the mean value is a x naught. Our initial state is always deterministic. These are assumptions that we make. So this is what we use for NCS, asymptotically stable in the mean square. Okay, so basically the same idea, except that you are saying the expected value of x minus xc, the equilibrium point, the norm of its square. So that is the Euclidean distance. Okay, is approaches 0 as k tends to infinity, then we call that asymptotically stable in the mean square, Lyapunov stable in the mean square, bounded in the mean square, bounded in the mean. So these are standard definitions in stochastic. Because of the stochasticity, you know, that you take the mean, expected value becomes the mean value, right? So some people use probability. So they say that asymptotically stable with high probability. So they are all the same. The probability between 0 and 1, they show that is close to 1, you know, all right? So, okay, now remember yesterday we talked about this optimal control. So if I have a time varying system, x of k plus 1 is ak, xk plus bk. A and b are time varying, right? So I want to optimize an infinite horizon value function v star, minimum of this. That is, the horizon goes from k to infinity. This is the quadratic term that's equal to x transpose pk times x. So the optimal control, you see that this is the Bellman equation. Okay. Now the Bellman equation, somebody was asking me what is temporal difference error. So you see that v of x of k is on the right hand side. I brought it to the left hand side. Okay. So I brought it to the left hand side. You remember yesterday we said v of x of k is the time to go from k to k plus 1 plus k plus 1 to infinity. It's a recursive equation. So what I did here is I brought the v of x of k from the left hand side to the right hand side, and the difference between this is called temporal difference. Why? Because the value function at x of k plus 1 and the value function at x of k, the only difference is this is k plus 1th instant, this is k. So a lot of times this is considered as a temporal difference error, or this term for optimality has to be 0. This is called the Bellman error. So in a normal circumstances, for optimality that has to be 0. But when you are using neural networks or some other approximators, it won't be 0, so you equate that to a little error, epsilon. And you use that information to tune the weights. So that is called the temporal difference error in reinforcement learning. You see? So that's basically because of the difference between k plus 1 and k. All right? So I'm going to use the word temporal difference error. You need to know that. Now, why is that temporal difference error we use? That helps us to make reinforcement learning approach for real-time systems. That is the reason. Because if it's 0, that means it's optimal. Okay? Remember we did that in calculus of variation, partial h over partial u equate to 0. That's exactly the same. And in real thing, you won't have a 0, you will have some value, and the goal is to drive that error to close to 0, and you will see that, I'll show you this Bellman error, you will see that going to 0. What is Bellman equation? This recursive equation is called Bellman equation. Okay? Any questions here? So from there you obtain the optimal policy. You see the optimal policy? The optimal policy, you need A, you also need B. And you also need kernel matrix P, which is the solution of the Riccati equation. And the Riccati equation also requires A and B. Okay? So here is the discrete time optimal control linear systems. If I have x of k plus 1 is this, here is the finite horizon n minus 1, and this Sn is the terminal weighting matrix, Q is the weighting on x, R is the weighting on the U. So when you increase Q and R, that means you are putting more effort. That means you are saying that my x is very important. This is for regulation. Regulation means you want to go from any value to any desired value. Okay, and so when you increase the value of the matrix, that means you are saying that it's very important for us, and you are driving that smaller and smaller, the error. Okay, so R is basically weighting the control input. So when you crank up R, that means you are saying that my U is very important. I really want really smaller values of U. That means I want to really minimize my U. Okay, so this is the Riccati equation, S of k, and this is the Kalman gain. This is the gain matrix. You can see which requires A and B, and then here is U equal to minus kk times x. For a finite horizon, the gain matrix Kalman gain is a time varying. Okay, so a traditional stabilizing control, usually we use k to be a constant. For optimal control, k has to be varying. That's the difference. Remember that. So for any system, even for A and B are constants, for finite horizon, k has to vary with respect to time for optimality. So that means that it's more computationally intensive compared to stabilizing control. Okay, so this is the same thing. How do you come up with those equations I showed you yesterday? X of k plus 1 is A and B. Then here is the value function. I can rewrite this as a recursive equation. Look at that, how I rewrite it. From k to infinity equal to k plus 1 plus k plus 1 to infinity. Now, if I move this v to the right hand side, this becomes 0. That becomes the temporal difference error. Reinforcement learning. So then what you do, you use a quadratic function for v, and you take that v of x of k plus 1, v of x of k, and from that last equation, right, and v of x of k is x transpose pk x of k, v of x of k plus 1 is x of k plus 1 transpose p of x of k, p of k plus 1 times x of k plus 1. But x of k plus 1 is given by this equation. So you plug all that stuff, then you get this Hamiltonian. Okay? Then you take partial of h with respect to u, then you get the same stuff. You take this and plug it back into the Hamiltonian, you get algebraic Riccati equation. It's very simple. So the same result you get whether you're using dynamic programming or the traditional optimal approach. Okay? Yesterday we saw these slides, but these were inserted for a reason. And you can see that you need A and B precisely. Okay? Doesn't matter whether it's a system is linear or continuous. So now stochastic linear discrete time control, basically you are taking this A x of k. Remember I said this is traditional with a process noise. Okay? So what is the difference between that and this? You follow the same. Okay, so you follow the same derivation, v equal to x pk x of k. You see an extra term here? That's what you're going to add if you have a process or a random noise. Okay, so you add that and you see that v of x of k plus 1 is this plus q of k plus 1. And why are you adding that? That's because you have the w, the process or process noise. This is the stochastic. Then you manipulate the Bellman equation, and you have two terms. One is you see that the same kk. So this is same as your deterministic term. Okay, there's no change. So if you look at it, the Riccati equation, you have pk, which is same as the deterministic, and you have another equation because of the noise, the w. You see that? So there will be two equations when you are going from deterministic system to a stochastic system, because essentially you have the process noise. Otherwise, the optimal policy is the same whether you are using a deterministic or stochastic. Okay? So that's important. So that's the difference between a stochastic optimal control versus a deterministic optimal control.